Hi, and welcome to the introductory tutorial to ALFA. ALFA is a plugin for Rhino that will help us to evaluate lighting design in terms of our circadian health and alertness. For this tutorial, we're using an open office Rhino file. We have a layer structure. I'll get into some of the details of this further into the tutorial. One thing to notice is that the ceiling object, the object display properties are set to wireframe, and that's so that we can look into the space while we're doing our simulations. So to run the first alpha simulation, let's just type in alpha. Now when we launch alpha, we are presented with a wizard which will walk us through the different steps in order to set up our first simulation. The first step is to choose the location. Let's just go with the Boston, Massachusetts climate file as the default. We can choose from a long list of different climate files that are different latitudes, longitudes, and elevations. We can set the month, day, and hour. We'll use the defaults for now, March 21st. We're going to start with a daytime simulation at 9 a.m., but later in the tutorial we'll set a nighttime simulation to rely just on electric lighting. We'll use the clear sky condition and uniform ground spectrum for now. The next step will be to set up the materials. So here we can assign materials by layer. Any layer that we have on in the Rhino file will appear in the alpha dialog box. If we turn off a layer, it's not going to show up. So we have some furniture objects in our office plan that we'll turn on later in the tutorial, and we'll assign layers to those objects later. But for now, let's just set the materials to some of the basic layers that are in our Rhino model. So let's start with, I'll hold on Control and select the ceiling, the column, and partition. Now let's choose a material for these three different objects. We can choose from opaque materials or glazing materials. We can subdivide by object type. And then here we have a list of different materials to choose from. I'm going to select the white painted room walls material. We can see the different optical properties of these materials by looking at these physical characteristics. So the specularity, the reflectance in the photopic range, and the reflectance in melanopic, and then the M/P ratio. You'll see photopic and melanopic and M/P appear a lot in this tutorial. These refer to, for the photopic, this refers to the human eye's visual response to light, and melanopic refers to the non-visual response to light. So in terms of reflectance, it's going to be, the material's reflectance in the photopic range or in the melanopic range, and then the ratio of the two. So I'm going to select white painted walls for these three materials. I'm going to assign selected materials to these layers. Now for the floor, I want a slightly darker material. I'm going to scroll down and select the light gray floor tiles non-slip for the floor. It has a lower reflectance value, both for photopic and melanopic. I'm going to select Assign Materials to Selected Layer. For the glazing, I'm going to select a glazing material. Now the properties have changed a little bit. We have additional columns for transmittance, both in the photopic and melanopic. I'm going to select the Double Glazing Clear TViz 63% for this material. For the mullions, I'm going to select, go again to the opaque materials. I'll select a dark gray color for the mullions. We don't need to assign anything to default or the grid large. This layer doesn't have anything on it in terms of the objects in the scene. And the grid large is just, we're going to use this later. It's a reference object to set up our grids in the space. So when we're done assigning materials, we can select Finish with Materials. Okay, now we can create luminaires for our space. So we're going to be using electric lighting in this tutorial. So we need to select the light fixtures that we're going to use. We first choose from different IES files that come with the ALFA program. We can click on Browse. This will open up the directory where the IES files are saved. We can scroll down to see different types of fixtures. I'm going to select the linear troffer lens 2 foot by 4 foot 5700 lumens IES file. Now we can also select the type of light source and the spectrum of that source in terms of a melanopic over photopic ratio. I'll pick a kind of neutral M/P ratio LED of 1, M/P, so that it's kind of a neutral fixture in terms of its spectrum. And we can see that the lumens in the photopic scale show up here, and the equivalent melanopic lumens are pretty close, and they appear here, 5690. We also see a photometric diagram in terms of the luminous intensity distribution curve for the light fixture. We can visualize that in this photometric diagram at different vertical section cuts by scrolling this slider. And then we have a graph that shows us the spectral power distribution for the light fixture. So we have the wavelength here on the x-axis and the radiant power per unit wavelength here on the y-axis, and so this dark curve shows us the spectral power distribution of the luminaire. And these different filled regions show us the spectral power distribution weighted over the visual response to light, so for the photopic response, and then the non-visual or circadian response, the melanopic action here in this filled-in curve here on the left. So when we're ready to add the luminaire to our Rhino model, we can select the Add to Rhino Model at XYZ Origin button here. Now this inserts the luminaire in the Rhino space at the XYZ origin, and we also have a layer that shows up in Rhino. You'll see that the luminaire comes with the photometric diagram. We can change the appearance of that diagram by using the scale slider here, or we can turn off the horizontal and vertical webs altogether for the luminaire. Now let's situate this fixture within the space. We're going to eventually be doing a nighttime simulation with electric lighting only. We want to have, for this tutorial, just an even distribution of electric lighting. So I'm going to first situate the light at the right height in the ceiling. It comes in at the floor elevation because it's the XYZ of 0. I'm going to move it. I know that my ceiling height is 3 meters in this space. So I'm going to set the elevation of this light fixture at 2.98 meters. So it's just below this ceiling. And now in plan, I'm going to set up a roughly equal distribution of light fixtures in the room. Okay, so our light fixtures are situated within the space. We can see them in perspective, kind of evenly spread out throughout the space. Now I'm going to go back to ALFA. So in ALFA, we now see that there is a list of luminaires that we have in the space. We have 15 of them, and they're all visible. I'm going to go to the next step in the wizard. So here we are prompted to choose our view position planes. Since we already have a reference object in Rhino, it's this plane. It's on the grid large layer. We also have some smaller grids, reference grids that we'll use to approximate more precise view positions at workstations later on in the tutorial, but we're just going to be using this larger one first. So I'm going to go to step 2, select planes in Rhino, left click that, and then we're prompted to select one or more planar surfaces. I'm going to left click the reference plane that I just mentioned and then hit enter. Alright, now this does a couple of things. So here we have our grid setup dialog box in ALFA. We have a nice little window that gives us a plan preview of our space showing the position of our grids. We can change the display of this preview. We can affect the line work of the different objects within the space. You can even do it by layer to have different ways of visualizing our preview display in ALFA. Now you can see that there are a couple of different types of grids of sensor types, and we can affect their spacing in meters by using this slider here. It sets the spacing between the grid points. I'll go ahead and just set that to 1.2. Now we have two different types of sensor points. We have view planes and work planes. The view planes are sensors that are approximating an occupant's view within the space, so they're oriented vertically. They're offset by default 1.2 meters, which is set to approximate the occupant's eye level when seated. And then these darker circles are the work planes. So these are horizontal sensors that are at the kind of table height. By default, they're 0.76 meters. Now, looking specifically at the view plane, this upper circle, we can change the directions, how many directions of view plane that we want for each of these. So if I zoom in here in this diagram, we can affect the number of slices or number of directions by moving this slider. So the lower the number, the fewer the directions there are, and the higher the number, the more directions there are. By default, there's 8. We can rotate those view directions. And just diagrammatically, we can change the size of how big they appear here in our preview. I'll leave it at 0.25, which is the default. I'll leave the default heights for both the view plane and the work plane. I'm going to click Finish for the grid setup, so we're out of the ALFA wizard setup. Now we have the default ALFA dialog box. So I'm going to go back to grids. Grids is where we're going to see the different metrics that we can view when we run a simulation by scrolling down here. So I'm going to go ahead and run a simulation. As you'll remember, we're running a clear sky condition on March 21st at 9 a.m. We can run our first simulation by clicking Start Simulation. Okay, when the simulation is complete, we can visualize our results in different ways under the Grids tab by choosing these different metrics, alertness, visual comfort, work plane illuminance. Let's just go back to alertness first. We can see that the different view plane sensors are color-coded in different ways as a result of the simulation. They're color-coded according to these categories, which are rough recommendations in terms of how alerting a lighting condition is for a specific view. This is characterized by the M over P ratio value. So we have a kind of average M over P for the entire set of view planes, which is 0.92. Then if we look more closely at the different view planes in terms of their directions, we can see that each has a different kind of category. The blue is an M over P ratio that's greater than 0.9. Now this threshold is set because there's a rough kind of general recommendation that M over P of greater than 0.9 will yield to a kind of alerting situation for this condition. If it's below 0.35 M over P ratio, that's generally speaking is going to be kind of calming. And if it's in between those two numbers, it's kind of neither calming nor alerting. These are just sort of rough general recommendations. Absolute illuminance values also comes into play, but this can begin to give us a sense of how alerting each view is. You can see that there's a high level of alertness because we have an average of 0.92. A lot of the view plane directions are really alerting, especially those that are facing towards the window where there's higher levels of light. Now we can also see that these values are previewed in the Rhino space. We can see that there is a kind of a spectral irradiance graph that appears as an average for the entire scene. It's giving us a sense of the irradiance per unit wavelength of the space. But if we hover over any specific view, that graph begins to change. That's going to give us the spectral irradiance for the specific view that we're looking at. We can actually also select any of these views, and by clicking on this camera button, we can run a simulation, a point-in-time simulation of that view. It opens up a new dialog box. It'll give us a visualization from that point of view. If I click the play button, I'll let this run. Now the simulation might take some time because there's multiple light sources, there's natural light coming in, there's multiple electric light sources. You can see that there's a fisheye lens kind of view that it's very sort of pixelated. It also looks kind of washed out. We can change the exposure level to lower the exposure so that we can view the rendering a little bit more intelligibly. Because the luminescences are so high, I'm going to set the exposure to, let's say, just 0.1. Here you can see that we can get a better sense of kind of the windows and the ceiling. You can even scroll around. It's going to be generating a view for kind of all the different directions for this view plane. It's going to take a while to run the simulation, so instead of letting it run, I'm just going to stop the simulation. We'll run another simulation when we're just looking at the electric lights. Okay. We can also look at the melanopic lux for each of these views. So you can see that there's an average melanopic lux, an average photopic lux, and I can visualize a false color by selecting this option. The default maximum is 500. You can see that the average is much higher than that. So if I just add another 0, make it 5,000, hit return, it will change the false color distribution on each of these view planes. Again, we have higher levels of lux closer to the windows, which makes sense. We can also define thresholds for the melanopic lux, percentage of views above a certain amount of melanopic lux. This refers a little bit more to the kind of Wells standard. We'll get into this threshold later in the tutorial. We can visualize visual comfort as well as work plane illuminance. When we click the work plane illuminance button, instead of showing those view planes, which are a little bit higher up at 1.2 meters, now we're only previewing the work planes, which are at the 0.76 meter height. Again, we have an average work plane illuminance, which is 7,625 photopic lux. I can increase the color legend threshold to 5,000 to see the distribution within the space in a little bit more variety. Now let's run a simulation just with the electric lighting turned on so that we can see how well the distribution of electric lights accomplishes a sort of more even electric lighting illuminance without relying on the windows. So I'm going to go back. I'm going to X out of the simulation actually. Simulation results. This clears the results. I could have saved them by clicking on the save button if you want to kind of compare different variants. But now this, by Xing out or saving, this allows us to go back into ALFA and change some of the settings in the scene in order to have a different kind of simulation. So I'm going to select location, and then I'm going to change the hour of the simulation. So instead of 9, I'm going to move it to a nighttime setting. So I'll just manually input 22. So that's at 10 p.m. I'm not going to change any materials in the scene quite yet. I just want to see how the work plane illuminance is in terms of photopic lux just by relying on the electric lights alone. So I'm going to go ahead and run the simulation again. Okay, when the simulation is complete, we now have results for the nighttime simulation relying just on the electric lights. The photopic lux false color looks very, very blue because the false color legend is set to a maximum of 5,000 lux. So I'm going to move that back to our default value of 500 and hit return. Now you can see that there's a relatively even distribution, some hot spots, some lower spots of photopic lux. If I move my mouse to any of these work plane sensors, I can see that the photopic lux number here in the dialog box will update, and it will tell me what the value is there. So this distribution of electric lighting is going to be sufficient enough for our next level of simulation, which we'll be looking at specific workstations, and we'll turn on the furniture and we'll look at the simulation results for views that are specifically at workstations within the space. So I'm going to go ahead and X out of the simulation. Before I choose the grid planes that are associated with the furniture, I'm going to have to actually go to the materials, and I want my furniture to appear in the space and appear in the materials list. So to do that, I'm going to turn the furniture layer on. The furniture layer has some sub-layers that have to do with desks, computers, bookshelves, and so forth. The monitor itself has some sub-layers, and I'm going to turn on the grid small reference layer. This is going to be, now instead of using this large reference surface to select a general room-sized grid, I'm going to use these smaller reference surfaces to select grid points that are just at the workstations. So now that I have the right materials turned on for the furniture, I'm going to go back into ALFA, and under materials, now you can see that the materials list has updated with the layers that I just turned on. I now have bookshelf, desk, and monitor, and so forth. So for bookshelf and desk, I'm going to change those materials also to the white painted room walls material. I'm going to select update. And now I want to assign some materials for the monitor. I want it to look a little bit more realistic. So for the glossy cover on the monitor, I'm going to select a glazing material. I'm going to select single pane clear glazing, update that. For the screen border, I want that to be a dark black material. I'm going to change material, go back to opaque. Let's look at the color swatches for the opaque materials. And I'll just go ahead and I want to just scroll down to the darkest materials. I'm going to click on one of these reflectance categories or columns and organize it by reflectance. And then scroll down to the lowest reflectance, DuPont Midnight Black. I'm going to update that. For the screen, I'm going to select neutral gray, so I'm also going to organize by photopic. Actually, I'm going to, you know what, for a neutral material, why don't I just click M over P? So I want that to sort of be just M over P of 1. I'll pick a M over P of 1, kind of a dark gray material here. I'm going to select update material, and then the metal body, I'm going to select a kind of shiny gray material. So I'm going to go to exterior materials, and I'll select this gray aluminum facade cladding, somewhat specular, and I'm going to select that. So now this will ensure that our furniture in the space here has materials to it so that they'll participate in the simulations, both for the grids as well as for when we want to have a view-specific visualization. I'm going to now select grids, Now I want to change the overall grid to a more workstation specific grid. So I want to change the reference material. I'm going to select grid planes, left click that. Now I'm going to choose the grid planes that are in front of each of the workstations. Okay, after I've selected these different surfaces, you can see that the view plane and work plane sensors have updated to snap to those specific surfaces that we selected. Now I want to configure them so that the view plane and work plane sensors are directly in front of each computer and that they match the number of them, so that there's four in total for each row of table, one for each computer. So to do that, I'm going to change the spacing. I know that my computers are spaced 1.6 meters away from each other, so I'm going to just update the spacing to be 1.6 from each other. So now you can see that there is a view plane sensor that's directly in front of each computer monitor. Now this is because I sized these rectangular surfaces so that they're overlapping with the overall location of these computers. So you just have to do a little bit of trial and error when you're setting up a new simulation for a custom workstation layout. One thing to point out, though, that these grid sensors start at the localized UV coordinate of each of these sensors. And so you can see that they begin here at the bottom right of each of these reference planes. And I've mirrored them in plan so that the lower left corner of the opposite aisle is going to be that kind of starting point for the next row of computers. Now let's limit the directions of the view planes so that they're just oriented one for each computer, so that each of them are facing each computer. So I'm going to change the directions of the view planes from 8 down to actually 1, so that I just have one view, a direction for each computer. But now you see that if I just look at the plan diagram, they're all facing in the same direction. They're all facing to the right. So I need to rotate half of the overall amount of view plane sensors so that they're all facing the corresponding computer. So I'm going to select the one column of view planes that I want to change, and then I'm going to hold down Shift, and I'm going to select the other ones. So these are all the view planes that are on the right side of each table. Now with every other row or column selected, I'm going to change the rotation. So you can see if I use the slider, I could rotate them 180 degrees. Just to be exact, I'm going to type in 180 here. And now if I unclick, you can see that they each are facing the right direction in terms of each are facing the computers here. So now I have one view plane that is at the right direction in front of each computer facing the right way. They're at the right height. So I'm going to run a simulation at nighttime to see what the results are in terms of alertness, melanopic lux, and so forth. When the simulation is complete, you can see that the results are now showing on the view planes. They're all within the alerting range, greater than 0.9. If I click on melanopic lux, you can see that the average for the view planes is 224 melanopic lux. Now I want to look at the percentage of views above a certain threshold of melanopic lux, or equivalent melanopic lux as referred to in the Well standard. So the Well standard has a couple of paths for accomplishing circadian lighting design. One of them is that if there's a space when there isn't any daylight, when you're working on electric lighting, that electric lighting should achieve 150 equivalent melanopic lux for all of the workstations at the vertical plane. So I want to change my threshold from the default of 200 equivalent melanopic lux to 150. The percentage of views that are meeting that threshold are 100%, so this would satisfy the Well credit. There are two ways to play with melanopic lux. The first is the spectrum of the light source, so the M/P of the luminaires like we were looking at before, and the second is the material palette. For the purposes of this tutorial, we'll keep the spectrum of the light source at 1, and we'll see how adjusting the materials affects melanopic lux. In addition, this will also allow us to see how changing the materials affects the way that we can achieve this Well score. So we can save the results. We could save these results as a kind of gray floor. For now, I'm just going to clear them out. I'm going to go back to materials. I'm going to look at the floor. I'm going to change that gray floor to a floor that is not quite as neutral in terms of M over P, but one that might be considered to be more on the kind of calming side. So a yellow painted stone tile floor has a much lower M over P than the gray floor, which had an M over P of 0.9. So let's change the floor to yellow painted stone tiles, which has a 0.34 M over P, less alerting, more calming. And I'm going to go ahead and run the simulation again and see how the percentage of views above 150 lux, equivalent melanopic lux, changes. Okay, when the simulation is complete, you can see that there was a slight effect in terms of the melanopic lux. Instead of being 100%, we're now down to 93.8%. Now this has a lot to do with how the scene is lit. In our case, we were using direct overhead lighting, but if we were applying these warm materials to, let's say, the ceiling and the walls, and we were using ambient or indirect light fixtures to cast light onto those surfaces, the material palette would have an even larger effect on the equivalent melanopic lux. Nevertheless, even though the change was minor, the percentage of views above 150 equivalent melanopic lux is now below 100%, and so the space would not achieve this particular feature of the well standard. So now I can select one of these views, and when I click the Open Render Window button here, we can initialize a point-in-time visualization from that particular view. So I'll click Start Rendering. And as the rendering is being generated, you could see that, like before, it begins as kind of pixelated view that will be increasing in detail and precision as the rendering makes more passes. We can change the exposure. You can see that there is a spectral irradiance diagram. It shows the overall photopic lux for this particular view, as well as the melanopic lux and the M over P. And we have the spectral irradiance graph here as a function of wavelength. And we can also see the photopic weighted spectral irradiance distribution and the melanopic weighted spectral irradiance. So as with before, we can pan around this view by left-clicking and just scrolling left or right. So it's not only taking the specific view direction that we chose, but we can also zoom around the space. And what's cool about this is that we can not only view this point-in-time visualization in RGB, we can scroll in this pull-down menu and display the false color in terms of photopic luminance values, or in melanopic or kind of circadian luminance values, which will be slightly different. So this wraps up our introductory tutorial to ALFA. Thanks for watching.